Now I would like to introduce our keynote speaker, Dr. Ellen Stofan, NASA's chief scientist. Dr. Stofan serves as the principal advisor to NASA Administrator Charles Bolden on all of NASA's science programs and science-related strategic planning and investments. Prior to her appointment at NASA, Dr. Stofan was vice president of proximity research in Maryland and is an honorary professor in the Department of Earth Science, University College, London, England. Throughout her career, Ellen's research has focused on the geology of Venus, Mars, and Saturn's moon Titan, and the Earth, having worked on a number of projects, including the Cassini mission to Saturn, the Mars Express mission, and the Magellan mission to Venus. In addition, let me point out that Dr. Stofan is very familiar with the peninsula. She received her bachelor's degree in geology from the College of William and Mary. Ellen, welcome.
Thank you very much. It's really a pleasure to be here today. Let's see. And to be talking at this anniversary, and thank you, Dave, for hosting us here at Langley today. And thank you, everybody in the audience and who's tuning in to listen. The story of Viking is really the story of NASA, doing something that nobody thought we could do and accomplishing it in amazing style. On a personal note, though, I wouldn't be here today if it weren't for Viking. Well, actually, my parents are in the room, so I literally wouldn't be here unless it was for them. But when I was 14 years old, and my father, who you're going to hear from later today, was in charge of the launch vehicles. So we went down and stayed in Florida for several weeks for the launches, which I did get to attend. And I went to some talks that they put on for families of the people who were working on the mission. And they had people like Jerry Stofan, Carl Sagan, talking about what I'm going to be talking about today: why we explore Mars, the mysteries of the red planet, the history of water, the possibilities of life. And I thought, wow, that sounds swell. I think I'll do that. And I decided right then to become a planetary geologist, and now I'm standing here before you today. So for me, Viking isn't just an amazing scientific accomplishment by NASA, an amazing engineering accomplishment. It's also an inspiration to all of us. And as we move forward to send humans to Mars, we're going to inspire that next generation of explorers and scientists. But for right now, I want to take you way back to talk about our exploration of Mars. And you know, that really goes back to the time of Giovanni Schiaparelli putting together this map in the late 1870s, early 1880s, putting place names on Mars like Mare Australe that still exists today. But of course, even at that time, mapping what he thought looked like canals. So while we have a lot of press conferences at NASA talking about discovering water on Mars, we've long had this association of water and the red planet. Now, fast forward from the 1870s to 1965 and Mariner 4. Now, just think about that. 1965, we traveled that 225 million kilometers and successfully flew by Mars and obtained images. Okay, blurry images, but images of the surface. The image of the left is around the area of Elysium. It's about 300 kilometers across. And the image and it's the first image taken of Mars. The image on the right is the first image of an impact, a clear image of an impact crater. It's about 200 and some kilometers across, taken on Mars by Mariner 4, beginning this long, long exploration of the red planet. Now we move to 1971 and Mariner 9 with this beautiful image of Nergal Vallis. Again, letting us know, as geologists analyzing this image, is that Mars was a place where the surface appeared to have been carved, much of the surface appeared to have been shaped or carved by water. When we see these valleys, they're very characteristic of river valleys here on the Earth. So already scientists were wondering, what is the history of water on the red planet? Why did it lose its water at some point in the past? And could that water, by any chance, have ever provided an environment in which life could have evolved? And because of those questions, because of this body of data that had been collected prior to Viking, we were able to design orbiting spacecraft and landers that could answer very focused questions that you're going to hear a lot more about today, about that history of water, the history of the surface, and the potential for life. So on August 20th of 1975, the Viking 1 spacecraft was launched, and I witnessed it. And then a few weeks later, the Viking 2 orbiter was launched from Cape Canaveral in Florida on the Titan Centaur. And then, of course, the event that we're celebrating today, July 20th, 1976. This is the first color image returned from Chryse Planitia from the Viking 1 station. And I understand that to a lot of people, you'd say, okay, wow, red plain, lots of rocks. But to the geologists who worked on this mission, right away they could start understanding that that hill on the distant horizon was actually the rim of an impact crater, that those rocks across the surface were probably excavated and dropped onto the surface when that crater formed. And that by looking at those rocks, by doing the chemical analysis of the surface, we could understand the history of this part of Chryse Planitia, a volcanic plain littered with impact craters, then carved by the wind later in its history. So by having these landers on the surface, making these measurements, we were able to start putting together the story of Mars. From the orbiting spacecraft, again, we really looked at these riverbeds, these ancient riverbeds. This is part of Mangala Vallis, which I mapped as a summer intern at JPL, I think in about 1981. I was a planetary geology undergraduate research program intern out at the Jet Propulsion Laboratory, and I was assigned to work with a guy named Dave Pieri and map this section of Mars. And what was so fascinating, again, were all these features that were so familiar from our studies of the Earth. Things like teardrop-shaped islands, abandoned oxbow sections of channels, features that by looking at rivers here on the Earth, we could understand that these features on Mars had been carved by water, and in some cases by great floods of water coursing across the Martian surface hundreds and hundreds of millions, if not billions of years ago. So as the scientists put together all of these different aspects of the Viking data, they started to understand the role that volcanism had played in the history of Mars, with the great volcanoes of Tharsis, the Elysium volcanoes, understanding how the plains of Mars had formed, and then understanding the role that water had played carving across those volcanic plains. And of course, also really understanding a little bit more about the composition of the surface of Mars, this very basaltic planet, these big dust storms that coursed across the surface, and of course here, the Great Valley that cuts across the surface of Mars. Now, many years later, it's amazing to me that we can literally look at the Viking landers. This is the Viking 1 lander, the Thomas Much Memorial Station, and this is an image that was taken by our HiRISE spacecraft in 2006, where it's a little hard to see on this image, but you can see actually not just the lander, but the back shell and what we think is the parachute and the heat shield, even up there in the upper right corner of the image. The same is true. HiRISE has also imaged the Viking 2 lander site in Utopia Planitia. This is the Gerald Stofan Memorial Station. And again, not just finding the lander, but all the bits that came off in the process of landing. So this allows us to take these very detailed chemical measurements that were made at the surface by the Viking landers and put them in a much broader context. And in fact, in general, that's what the Viking mission allowed us to do. It allowed us to look at all of Mars and put it in what we call a geological context. Now, this image probably doesn't mean a lot to a lot of people in this room or who are watching, but to a geologist, this is everything. And this is the compiled geological map that was put together of Mars by people like Ron Greeley, John Guest, Ken Tanaka, Dave Smith, who mapped from the Viking orbiter data, produced a geologic map of the entire surface of Mars. So to a geologist, all of these colors are basically telling us what rock layers formed when. It's allowed us to create a history of Mars, and by counting impact craters on the different units in this geologic map, we are able to put time to that story so that we understand what happened when in the history of Mars. This is the detective's guide to Mars. It allows us to say, we understand the history of the red planet. And again, all of this was done based on Viking orbiter data, really allowing us to understand the history, the overall geologic history of the red planet. But of course, that's not the end of the story, because every time NASA flies a mission to another world, and sometimes the engineers and maybe some of our stakeholders get frustrated by this, we end up with more questions than we had when we formulated that mission. So this Viking map, the Viking data, the Viking chemical results from the landers, that wasn't the end of the story, that was the beginning of the story, because that allowed us to formulate more complex questions. Okay, there was water on Mars, but when exactly did that water flow on the surface? How long did it stay on the surface? What was the chemistry exactly of that water? Was it acidic? Was it basic? Would it have been conducive to the evolution of life? So all of these questions, the Viking data allowed us to formulate them, and then allowed us to design future missions to Mars, which we've been operating since. And that video gave you a good sense that we saw earlier, gave you a good sense of some of what's gone on afterward. Right now on the surface of Mars, we have two rovers operating, the Opportunity rover and the Curiosity rover, moving across the surface of Mars, making measurements, trying to, again, get at those very specific questions about the history of water on Mars that the Viking mission allowed us to formulate. And you're going to hear a lot more about the results, especially from Curiosity, later today. So it really has been about following the water. But from Curiosity to the InSight mission we have planned to launch in 2018, to the ExoMars rover, which will launch in 2020, along with our science rover in 2020, we're really changing gears. We're not just trying to get at answering these questions about the history of life on Mars. We're also getting ready for the next stage of Mars exploration, which is getting humans to the red planet. So when we landed the Curiosity rover on Mars, for example, we were taking measurements as we descended through the atmosphere to help us better design future entry, descent, and landing systems that would be carrying much heavier payloads, things like people. We've been measuring with the Curiosity rover the radiation environment on the surface of Mars, trying to make sure that we understand how much radiation a future astronaut on the surface of Mars would get. And we've put that planning very much into the Mars 2020 rover, and again, you're going to be hearing more about that rover later today. Curiosity, I think, for me, has been a rover that's really put us into the surface of Mars. It's put us into that framework. It's made us the Martians, because it's given us this beautiful, incredible landscape that as Curiosity has slowly reached the base of Mount Sharp and started to climb, analyzing those layers of rock in Mount Sharp. And remember, for the geologists who work on the mission, each of those layers of rock is like a page in the history of the story of Mars. And so they're reading each of those pages and helping us to unravel what happened on Mars when was the water present, what was the characteristics of those water, and would that have been an environment conducive to life? Because life here on Earth evolved in the oceans, and it stayed in the oceans for well over 1 billion years. So when we want to answer this question of, is there life beyond Earth, going to this watery planet, where we now know from Curiosity that water did persist for long periods of time on the surface of Mars, this is critically important. These findings we've been making have been critically important. So if life did evolve on Mars, our MAVEN spacecraft has told us that Mars eventually lost its atmosphere, the planet became cold, and the water retreated underground. Some of it was lost into space. So as the water retreated underground, we have an ongoing question. Did life persist on Mars, or did it go extinct if it evolved? So we were very excited about a year and a half ago when our Mars Reconnaissance Orbiter found these funny brown streaks that you see on the surface of this image of Mars. Those brown streaks were actually indicating that seasonally we were getting liquid water percolating up to the surface, running down steep slopes that were facing into the sun, so you'd get melting of subsurface ice, and that water would run down the slope. Now, okay, that's cool, but it's really important from a scientific point of view. That means we have the potential to access that subsurface water on Mars quite easily. And so again, it goes back to this question. If there's life on Mars, that's probably the environment in which we would find it potentially in the future. So these are extremely exciting sites for potential future exploration. President Obama has given NASA a goal of, by the mid-2030s, getting humans to the vicinity of Mars, returning them safely to the Earth, and then sometime following the early 2030s, landing humans on the surface. And so that's NASA's goal, and we're working really hard every day to make this a reality, and we can do it. Now, why humans? Why not just keep our amazing robotic exploration going? Well, I'm a field geologist. I go out to volcanoes around the world, pick up rocks, and I have this conceit that we need field geologists on the surface of Mars, because finding life is going to be hard. When I'm talking about life, we're not talking about dinosaurs here. We're talking about fossil microbes. They're going to be really hard to find. Any of you who have ever looked for fossils on the Earth know they don't just pop out at you, and this was a planet which had extremely rich life. So finding life on Mars is not going to be easy, and that's why we haven't found it yet to date. So I think you need geologists, astrobiologists, chemists on the surface of Mars, cracking open a lot of rocks, going to the right locations to really determine not just did life evolve on Mars, but what is the nature of that life? What can that life tell us about the evolution of life here on Earth? Does it have cell structure like ours? Does it have RNA? Does it have DNA? These are the fundamental questions that we want to answer by looking for life on Mars. So you're going to hear a lot about this today, our journey to Mars. Because to do such a difficult thing, send humans that long distance to Mars, you need to do it in a stepwise fashion. So we are working right now on the International Space Station. In the mid-2020s, we'll move out to the vicinity of the Moon, and then on eventually to Mars by the early 2030s. But obviously in the meantime, we're not stopping exploring Mars. We're still every day getting data from our spacecraft at Mars, and we will send spacecraft to Mars in the future. And the road to Mars really does begin at the International Space Station, and I'm going to talk a little more about this later this afternoon. Because to me, one of the hardest parts of getting humans to Mars is coping with microgravity. And that long 7 to 8 month journey back, or to Mars and then back, is a long time for humans to be in microgravity. And that's why Scott Kelly's one-year mission has been so important, and that's why the work that we do every day on the International Space Station is so critical to getting to Mars. But to some extent, we also need to step back and say, what do we already know how to do? We know how to get spacecraft to Mars. We've landed on the surface of Mars 8 times. We know how to maneuver spacecraft in deep space. Look at the amazing dances that the Cassini spacecraft has done around Saturn. NASA's really good at that. We've learned about entry, descent, and landing on Mars, but with much smaller size payloads. We need to ramp that up. We've learned a lot about the dust on Mars, about the potential toxicity of the Martian environment to humans. But there are definitely more measurements that we need to make, and there are definitely more things to do. So we will continue again through the 2020s exploring Mars and then getting ready to send humans onto Mars. So right now, we're looking in the early 2020s. We'll need to send an orbiter to Mars, and NASA just this past week selected some concept studies for orbital orbiters. We need that partially as a communication link to talk to our rovers on the surface. But if we can also be making some measurements, taking some data that will help us get humans to Mars in the future, we'll do that also. At some point in the 2020s, we need to do a round trip from Mars to Earth robotically to practice ascending off the surface of Mars, rendezvousing in orbit, and returning to the Earth. And obviously planetary protection, understanding what those rocks are on the surface of Mars, their potential for contaminating the Earth is something that we really want to understand before we actually send humans to the red planet. So in the mid-2020s, we'd like to do this round-trip demonstration mission to Mars. And then, of course, we're also very interested in something called ISRU, in situ resource utilization. That's, can we use resources on Mars to either help astronauts on the surface of Mars or even help us get back off the surface in terms of doing things like producing rocket fuel on the surface. But don't get me wrong, Mars is hard. This is a real challenge that we have in front of us. It's a really long distance to send humans. Time in microgravity is not easy. We get bone density loss, muscle wasting, there's radiation exposure. So again, that's the work we do every day on the International Space Station to buy down those risks. And in the mid-2020s, which you'll hear more about later, we'd like to put a habitat out in the vicinity of the moon that will serve as the prototype for the Mars transfer vehicle. And we'll do more research to understand that long-term effects of mixed field radiation, which is what you get out in cislunar space. You get a combination of radiation coming from the sun, which we're very good at shielding against, and you get radiation from galactic cosmic rays, which we have a very hard time shielding against because they're such energetic particles. There's a huge comm delay at Mars. You have up to about a half-hour comm delay. Now, obviously, that's hard operationally if you have humans on the surface, where we're used to on the International Space Station being able to talk to the astronauts anytime we want very quickly. But it's also actually hard for astronauts' mental health. Just think, you want to talk to your family. Your family on the Earth says hello. An hour later, they hear, what? So this whole issue of the long-distance communication, how we accommodate that from the astronaut's point of view, from an operational point of view, is something that we need to work on. Of course, we need to get cargo to Mars, so there's the aspect of that. We come in very fast. Right now, we don't know how to land very large payloads on Mars, but we're working on it. And this whole issue of, can we use Mars resources, for example, to manufacture rocket fuel? The first step toward Mars, you're going to really see, the first step is always going on the International Space Station. But in 2018, we're going to take a giant step forward. And that's when we're going to launch for the first time without a crew the Space Launch System, our new rocket that we're building to get humans out beyond low Earth orbit, with the Orion capsule on top. That first mission will just go out around the moon, orbit, come back, descent, and land back on the Earth. But this will be an incredibly important milestone. We need that heavy lift launch vehicle to move humans out beyond low Earth orbit, where we've been now for so long. So every day, we're working on the technologies that we need to go to Mars, things like solar or electric propulsion, things like how do we decelerate in that Mars thin atmosphere. How do we live on the surface? We look at prototypes for how we might rove with humans on the surface, how we might have habitation modules for humans on the surface. How do we feed astronauts on the surface of Mars or on these long space journeys? We're working on these technologies every day at NASA. But I really wanted to come back to the point that when we're doing this, when we're preparing for this journey to Mars, it's the people of NASA who are working on these technologies. It's the people in our contractor families. It's our international partners. It's the private space sector that we partner with. It's all of these people who are doing the hard work, who are dedicated, who really believe in this vision of getting humans to Mars in the early 2030s. So it made me reflect back on, it was the people of Viking. You're going to hear a lot about cool data today. You're going to hear a lot about the amazing findings we've been learning about from Curiosity, what we're going to do in the future. But it all really rested on those people of Viking who built the launch vehicle, who built the spacecraft, who designed the instruments, and who interpreted the data. Because as an agency, a lot of the times we talk about our stuff, our rockets, our spacecraft, but it's the people behind all those things who are really accomplishing these amazing things. So today really is all about the evolution of a Martian. From those early days in 1965 with Mariner 4, all the way through Viking up to the present day and our Curiosity spacecraft and our vision of getting humans to Mars in the early 2030s. It's this path that we're on. And again, Viking was such a critical hinge point in that of really allowing us to see Mars was a wet planet, water was present for long periods of time on the surface, and Mars has the potential, more than any other place in this solar system, of helping us to answer this question of are we alone in our universe? And we now know from all the data that we are on the verge of answering this question, and we will get humans to Mars in the 2030s. Thank you.